So on a Tuesday after next.
Tuesday after next? Okay.
Yeah. Okay. Excellent. Fine. So apart from Ronald's lecture, which we will have in the next class on the tree-level scattering of gravitons, we're basically done with our discussion of tree-level scattering in the boson. Of course, tree-level scattering in the superstring is a bit different. The ideas are more or less the same, but the formulas are a bit different. But every qualitative thing that we've talked about, apart from the existence of the tachyon pole, of course, goes through in the tree-level scattering of the superstring. And so that, right. Okay. Now, we will get to that next semester. When we study superstring theory next semester, we will try to understand scattering of the superstring. Okay, now I want to begin a discussion of one-loop amplitudes in string. Okay, one-loop amplitudes are the only kinds of amplitudes we will discuss in class that go beyond 3 levels. Firstly, for technical reasons, to try to do two-loop amplitudes is extremely difficult. And secondly, for physical reasons, while what we're presenting might seem very technical and detailed, it is of course just an introduction to it. Okay? We're not at all touching on everything that's not about string theory. So the purpose of the course is to try to give you an introduction to every basic thing, so that when you want to learn something particular, you have the background to do it. And also to introduce you to every basic physical concept. More important, that appears. So, when you, some question that you think about when presenting a new calculation is what physics is teaching. Okay? So we saw a lot of physics in the tree-level scattering of tachyons. We'll see the same physics when Ronald tells us for the tree-level scattering of gravitons. Okay? And what we're going to see also when we study the tree-level scattering, one-loop scattering of strings, we'll see an enormous amount of physics, okay, which will allow us to understand various consistency things about strings. You will see that there will be a great deal to learn physics-wise by studying these one-loop amplitudes. And actually, we can learn most of this physics by studying the simplest one-loop amplitude, namely the vacuum amplitude, the amplitude with no insertions. Okay, so. But before I get to that, I have to deal with the technicalities. Okay, so this goes studying the torus. We will soon generalize to the cylinder. To the cylinder, and we will also, by the end of these three, I was planning 3 lectures on the subject. By the end of these 3 lectures, we will also generalize to unoriented strings. We'll be forced to, for example. Okay, but let's start with the simplest case of the concept reason. In this case, we will have the torus. Okay, so what is the torus? So, a torus can be thought of as in one-to-one correspondence with a lattice in 2 dimensions. Okay, so a lattice, as you know, is a set of points that are generated by linear combinations of 2 basis vectors. Where the linear combinations are combinations by integers, positive and negative integers. Okay. Now, we're interested in the geometrical shape of the torus itself, not its representation of the plane. So we can always rotate our lattice. So one of the set of lattice vectors lies around the x-axis. Okay. And we will be interested in shapes up to scale transformation, up to conformal factor, up to Weyl transformations. So an overall factor outside the metric will not bother us. So using that, we can always scale the lattice vector in the x direction to have length 2 pi. This is the convention we will adopt to, of course, it's the standard convention. Okay? So, this lattice, one of its vectors is 2 pi here. And the other vector, what's the other vector? Well, the other vector is whatever it is. It's some complex number which we call 2 pi tau. Okay? So for us, the torus will be power of, as given by the metric ds squared is equal to dw bar with this identification. W is to be identified with W plus 2 pi, and W is to be identified with W plus 2 pi tau. And tau is an arbitrary complex number. Because if tau is a real number, that's a degenerate torus. The tau 2 should be constant. We'll often write tau is equal to tau 1 plus I tau 2, and we'll require tau 2. Okay. Now, very shortly, we are going to show, and we're going to show in detail because we know for the calculation. Very shortly, we're going to show that tori, in fact, maybe I should just do that. I want to argue that tori with different values of tau are conformally equivalent. Okay? That torus with a different value of tau cannot be recast by a coordinate change. It does not have a metric which is the metric of the original torus times an overall vector. Now, this discussion is a bit subtle because we've got these periodic identification of coordinates. Okay? So when I say it cannot be recast into a metric which is an overall y factor times the original metric, I mean on the same space of coordinates. Okay? Because you see, what we have is two different tori with different values of tau won't look like they have the same metric. It's dw bar, but that's a fake. Because one set of w's runs over a certain region. The other set of w's runs over a different region. To be able to compare the two metrics, we have to move to coordinates, but both coordinates run over the same region. And then we can compare the metrics. Okay? We want to be on the same manifold. And then we want to compare the same, we will compare the metrics.
dw bar on the plane?
Yes.
So in what sense are the two, still looking at the metric on the plane, right?
We're looking at the metric on the plane, but they run over different regions. Another way to say it, if this makes you more comfortable, is that when we've got, how are you supposed to look at a manifold? You're supposed to look at a manifold as a union of patches, each of which is an open neighborhood of R2. And then you're supposed to make the whole torus by gluing together these patches and specifying the transition functions. So, we get around all of that as physicists by just specifying some periodicity. But when you change the periodicity, what you're doing is changing the transition functions. Okay? So, if you want to think of a manifold formally like a mathematician, this is not what I ever want to do. Okay? But just to say, for people who are not in that language, you think of it, let's say a torus you can make up by 4 patches. Let's say a circle, for instance, to start with, you can make up by 2 patches. That's clear, right? And similarly, a torus, then you'd have 2 patches with some thickness here. Okay? So you can make up a torus by 4 patches, and you would, in each of these patches, it would be like R2, and then you would have to specify transition functions. The transition functions basically tell you what the periodicity is. It says that this guy is the same as that guy. Okay? So, the point is that you work with coordinates with a given periodicity, and then you can compare the metric. That's in the end of the net result. Okay? This goes into your data of specifying what the manifold is, the periodicity, before you even start talking about a metric. Okay?
Can we say it more physically in a physical way? So a torus is equivalent to a parallelogram on a 2D plane.
Is equivalent identification by a parallelogram.
Yeah, and if the value of tau is different for the same base 2 pi,
yeah.
So you cannot bring it to the first parallelogram without changing angles.
Yes. The identification I have. The only issue is it's about identification. Yeah, you're right. You're right. We're going to see this very in great detail just now. Okay. So suppose we've got a set of coordinates such that W is equal to W plus 2 pi and W is equal to W plus 2 pi tau. Now we've got another set of coordinates. Let's call them W prime. That's that W prime is equal to W prime plus 2 pi and W prime is equal to W prime plus 2 pi tau prime. I want to know what is the coordinate change. I want to find at least one coordinate change between W and W prime. Okay, I want to write W in terms of W prime so that the identifications map to each other. I would also like to make the coordinates change, such that okay, I'll find at least one coordinate change. Let us. It's clear we can do this by doing a linear coordinate change. Okay, that's clear because we're just changing identifications. So suppose we have W is equal to A W prime plus B W prime bar. And that's the key point. Key point is we'll never be able to get the identifications to match without having W also a function of W bar. That's the essential point. It's not an and it. That's the main thing of this. Okay? So that W bar was equal to A W prime bar plus A bar W bar plus B bar W prime. Okay? Now, we want to know what values of A and B will work to get the identifications right. Okay? So, what we will do is to orient the tori so that 2 pi maps to 2 pi. I'll talk about that in a moment actually, but modular transformations and so on. But let me quickly do this. So, when W prime changes by 2 pi, we want W also to change by 2 pi. It's clear that means that A plus B is equal to 1. Because when W prime changes by 2 pi, W prime bar also changes by 2 pi. Because 2 pi is real. So this whole thing changes by A plus B into 2 pi. Okay, that only works with A plus B. So, is this clear? We also want that when W changes by tau, W prime
B, sorry, A plus B equal to 1 or A plus B tau is equal to 1?
No. We want 2 pi and 2 pi to match each other. So when W prime changes by 2 pi, we want W to change by 2 pi. No, tau is not entered. Okay? Now, we want that when W prime changes by tau, tau prime, thank you, W changes by tau. So we want that tau is equal to A tau prime plus B tau prime bar. Is this clear? So we have to solve these two equations simultaneously for A and B. So let's first do it for finite A and B, and then we'll stick to infinite. Then we will, our main interest will be infinitesimal changes of tau, which we will try now. Okay? So let's solve. In order to solve the equation, what we do is to multiply for the first equation by tau and subtract. So we get B, we get tau minus tau. If I multiply by tau and subtract. No, what I mean? I multiply by tau prime. Yeah, I multiply by tau prime and subtract. So if I multiply by tau prime and subtract, I get B into tau prime minus tau prime bar is equal to tau prime minus tau. Okay? And so we get d is equal to tau prime minus tau prime bar over tau prime minus tau. Similarly, if you wanted a, we would multiply by what? You got tau prime minus tau.
No, numerator is the same.
Sorry. This first I multiplied by tau prime. So tau prime minus tau prime bar should tau prime minus tau prime bar should be here, and here it is tau prime minus tau. That's correct. Excellent. Now I have multiplied the whole thing by tau prime bar, and then subtract. I will get a is equal to tau prime bar minus tau over tau prime bar minus tau prime. Did that right? Okay. Excellent. Okay, let's check. Suppose tau prime is equal to tau. Then we should get a is equal to 1 and b is equal to 0. Tau prime is equal to tau, a, b is 0. And if tau prime is equal to tau, this becomes tau bar minus tau over tau bar minus tau, which works. Okay,
So what did you check?
I checked that I get identity. That a was 1 and b was 0 if tau prime was equal to tau. Yeah, as it had to be, right? I'm not really sure. Okay, excellent. Now, suppose I put this quote, the main issue here is that b is not 0. If tau prime is not equal to tau. Do you see therefore that now if I plug in the change, suppose I took the metric, okay, dw, let's say I put dw, actually, anyway, suppose I take dw prime bar. Okay? And then I substitute what w prime is in terms of w. Well,
We wrote the equation for the.
Yeah, exactly.
dw bar.
okay? Suppose I take dw bar. And I substitute for w's in terms of w prime. Okay? I substitute for w's in terms of w. So, what is the point? Suppose we've got one torus with the identifications of w, another torus with the identifications of w prime. So one torus with tau, the other with tau prime. I take the torus with the identifications tau, and I write it in terms of coordinates, which have the identifications tau prime. Then I change the metric. Okay? And the changed metric, can you see, will have, in addition to a dw prime bar piece, will also have a dw prime square and a dw prime bar square. You can see that, right? Because that's the fixed thing. It comes from the B. That is the key point. So clearly then, this is some overall factor, because it's just constants, but the relative numbers have changed. So it's not conformally equal. It's not an overall factor times the prime symmetric, which was dw prime bar. Now, we need to understand this a little better. We need to understand this in a little more detail, because insertions of the weak host into the formula for string scattering have these factors of B, del tau, G, W. So we need to know not just qualitatively that the metric changes when we change tau, but we need to be able to compute the derivative of the change of the metric with respect to tau. Okay? So now let's work this out in detail. Since we're only interested in derivative, so we can get away with taking the change between the two taus to be infinite. So let's work this out in detail for the special case when the change between the two taus is infinite. Okay? So suppose tau prime is equal to tau plus delta tau. Okay? Then what we get? We get B is equal to delta tau, and this is tau prime minus tau prime bar, which is the same as tau minus tau bar, which is 2 tau, 2I tau 2. Tau is tau 1 plus I tau 2. Okay? We've already got an infinitesimal, so the difference between tau 2 and tau 2 plus delta tau 2 makes no difference. Is this clear? Okay. And A is equal to, well, we like to complete this triple non-vector.
Sir, how can you try to see
What?
by this infinitesimal transformation?
We're going to try to compute the derivatives of the metric with respect to the complex structure dynamic.
Okay. So you want to find the transformation.
We want to find the transformation so that we can eventually find the metric. You see, we're going to find the metric by performing the coordinate change, starting with the unit. Hang on. Okay? Let's also compute A for B. It will not matter. 1 minus B. Okay, good. So it's 1 minus delta tau by 2I tau. Okay? Now let us remember how did we do? We did W is equal to A times W prime. So 1 minus delta tau by 2I tau 2 W prime plus B delta tau by 2I tau 2 W prime bar. And the complex conjugate of this gives us the other. In case we need the other way around, we just flip delta tau to, we have tau prime is equal to, if we want W prime, we just flip the sign of tau. 1 plus delta tau by 2I tau 2, W plus delta tau by 2I tau 2, W prime, W.
Actually, writing might be on this.
Excellent. Okay. So now we want to know how.
Wait a second. Going back to the transforming between torus, are you saying that if you can deform the first lattice to the second lattice using conformal transformations, they are the same torus, otherwise they are not?
No, if you can deform the first lattice to the exactly. But it should be a conformal transformation. That's okay.
That's all.
Yes. And you see that we can do it, but without it's not conformal
Yeah.
because of mixing with W. Okay. So now we want to know how the metric has changed when we do tau to tau, tau plus tau prime. Okay. So what was the new metric? It was dw prime bar. But we want to express it in terms of the W coordinates, which are the right periodicity. So we plug in this formula. Okay? So, well, what do we get from here? See, okay, so when we plug in this formula, we get a term where we use this and this. You know, this guy for both W and W bar. That will give us is equal to 1 plus del tau by 2I tau 2 mod square dw bar. But we also get terms where we use this fellow. Okay? This is already infinitesimal, so we use one of these. Everything else is 1. Okay? So suppose we use that W bar, we would get dW square with a minus delta tau bar, with a plus del plus 2I tau 2. A plus because I star is I. Okay? That's what we use this in the W bar transformation. If we used it in the W transformation, we get dW bar square with minus delta tau by 2I tau. Is this clear? Okay. Now, what was our formula? Do you remember what we had was this B inner product with del, what we had del by del Pi, the moduli. Del Pi GWW. Okay? And then of course we had B bar with del by del Pi GW bar W bar. These are the two quantities we need to evaluate in order to evaluate the insertions into our bar. Okay? The first thing we say is that GWW has no derivative with respect to tau, but only with respect to tau bar. Okay? So we use complex coordinates of the space of tau, t's. Instead of thinking of the real and imaginary part of tau, we use tau and tau bar, which is linear transformation. Okay? We see that d by d tau GWW is 0. So only the tau bar that contributes. Okay? So we require really to have an insertion of this for every modulus. Insertion of this for every modulus. But one of the nice things we see is that the moduli themselves split up into those that contribute to the holomorphic sector and those that contribute to the anti-holomorphic sector. Okay? So, even in this insertion business, we can do it we can split the holomorphic and the anti-holomorphic part. Okay? The holomorphic part cares only about, in our language, tau bar derivatives. The anti-holomorphic part cares only in our language, tau derivatives. One could have flipped that language. Okay? So let's look at the holomorphic part. Okay? So let's look at the holomorphic part.
You will actually express the tau 2 in the denominator as tau minus tau bar or something like that?
We could. We know what it is. Yeah, it's tau minus tau bar or something like that. Fine, right? I mean, in order to calculate the derivative, we don't care. We only have. This already has a delta tau. So you're not differentiating the tau 2. Okay? So, what we see is that d tau bar of GWW is equal to 1 over 2I tau. Okay? And d tau of GWW bar is equal to 1 minus 1 by 2I. Is this clear? Okay. Now, some of you may be wondering, well, you could have done some further scaling to set this guy to 1, for instance. Would that have changed the result? Answer of course is no, because this was already proportional to something infinitesimal. So you multiply by 1 plus infinite. You see that it's a robust result, right? It's independent of any convention for how you. Okay, excellent. Now we understand, so now we take these results and we will use them.
Suppose it wasn't robust, would it be required?
No formula that is not robust should enter your string scattering.
Maybe not that way. Suppose this, the derivative, suppose 1 plus something there. And so basically suppose doing the y transformation actually change the derivative. Would you need to do the y transformation and then put in the derivative, or put in the derivative before the y transformation?
Now you see, what was our original idea? Our original idea was that for every modulus we need to specify a sample metric. One metric in that y class.
Right. So you need to do the y transformation.
Yeah, you don't need to do the y transformation. Or well, you could have said that I was specifying that y metric. Okay. The thing is that if it had depended, it would have depended on which cut you were taking. Which we proved on general grounds cannot be the case. So it would have been a contradiction. It shouldn't have. Okay? Great. So exactly. So this dependence or not is just specification of which particular metric in the y class you're choosing. And if the formula for string scattering depended on that, are we sunk? Okay? Great. So now we're going to complete this. We're going to complete our formal program of writing down a formula for string scattering amplitudes on the terms. This was the most, let me just check the bullshit case the same formula. Epsilon, so that's there. I just can't understand case notation. Epsilon star, which is the change in GWW. I'll just write down what he says and then we just check. Epsilon is equal to delta tau divided by minus 2 pi I tau cube. Now epsilon is the change in GWW bar. Same, right? Pi. Yeah, where did we get pi?
There is no pi in the formula.
But he might have taken his scaling to 1 instead of 2 pi.
Yeah, he says tau by pi. Just a minute.
No, then it should be 4 pi, right?
Just a minute. You know what? Yeah. Sorry. No, sorry. I just wrote it. There was no. It's 7.2 per 1 thing was no. The vice cancel. Yeah, sorry. It's just exactly. Good. Okay, good. So, Polchinski agrees with us. Okay, excellent. So, formal formula for the one loop amplitude, for the torus one loop amplitude. So what are the elements that went into the formula? See, we needed two vertex operators to fix because the number of killing vectors was 2. Do you remember on the torus there are two conformal killing vectors, which are just translations of the two sides. Okay, and the number of conformal, whatever the number of moduli is also 2 tau and tau 1.
Is that two complex killing vectors?
No, one complex.
Yeah, one complex.
One complex killing vector, one complex modulus.
Oh,
Yeah. So, right, exactly. Okay. So we need to fix two. We need to fix the position of one vertex operator. That's what it is. Thank you. One vertex operator. We need to fix both its analytic and its activity. Good. And we need to fix the. And we need to put the insertions for the modulus. Insertions for the modulus we've understood. So we had integral d2 tau. Right? Because d tau bar. This was the space, the measure on the moduli. And then we had this b times this derivative, okay, which was 1 by 2 I tau 2, but otherwise just a constant. Okay, and the integral b bar 1 by minus 2 I tau 2, but otherwise just a constant. Okay, this was integral d2w, and this was also integral d2w. These were the B insertions. Is this clear? B and B bar insertions. Yes, this was B bar. B bar. So this is B of W, this is B bar of W. Okay? But in addition to all of this, we also have the fixed vertex operator, which was C. Let's say that we fix it at 0. Somewhere. Okay. C of 0, C bar of 0, this V, this vertex operator, whatever it is, which is fixed at 0. And then we've got the product of integrated vertex operators for all of these. So B2W, whatever. D2W, B1, D2W1, D2W2, B2. Okay, I've written it very schematically, so you understand, right? Each time you understand. Anything that's unclear about this summation? Okay. Now, for the overall factor that comes into this, as for the overall factor of the sphere, we will depend on some consistency requirement to fix that. So overall factors we will not be very careful about. Though Polchinski claims to have got the overall factors right, surely that's bad calculation. You wouldn't believe that if you I mean, after you know the answer. But so it's not worth that. It's like factor of half because the W goes to minus W flip. I'm sure it's right, but you would trust it with the consistency check. So we'll keep the overall factor as something to be fixed by consistency in a minute. Okay? But factors of tau 2 are very important because they give you the measure moduli space for the integration of a module. So the things that we have to keep careful track of here are the factors of the tau. Everything else is overall, and we'll. Okay. Now, so So let's look at this. Firstly, this looks like a complicated thing. To start with, it looks complicated because we've got B of W. Okay, I mean, it looks like we cannot explain the tau 2 dependence of this because it's a B of W. However, notice, do you remember that the insertion of B contributes only by the zero mode? Okay, and what is the dependence of the zero mode of B? It's a constant. Okay, therefore, this insertion is independent where you insert B. Do you understand this? Let me say it more clearly to make sure you understand. This B of W can be expanded as B of W is equal to sum over n Bn. This is the Grassmannian integration variable times Fn of W. When these are the eigenmodes of the BC Lagrangian of the operator, the del bar operator in this case. Okay, the eigenmodes of this of the kinetic term that appears in the BC Lagrangian with eigenvalue En, whatever. Okay, when we do the path integral over B, we're doing the path integral over each of these Bn modes. Now, the mode B0, which multiplies the Fn's, which are zero modes, multiplies the Fn's that are zero modes under the ghost kinetic term, appears nowhere else in the path integral but in the insertions. So the only way that we get a non-zero path integral is if we soak up the contribution of B0. So in this expansion, the only term that matters is B0 times F0. Remember, we've been through this before. So there are other terms which depend on the detailed dependence of Fn of W's, so they don't contribute. Okay? So the full dependence of W of this insertion is the dependence of Fn of W. But F0 of W in this particular case happens to be a constant. Got it?
How do you see that?
How do you see it's a constant? Oh, you see it's a constant because this B is just the how do you say it's a constant? Okay. Let's remember what the operator was. Okay, what was the ghost Lagrangian? Okay, the ghost Lagrangian was B del bar C.
We were supposed to meet at 11.
No, sorry. Oh, yes, we were supposed to meet. I forgot I had a class now. Could we do it after class?
Yeah.
I'm sorry for it.
Yeah, no problem.
Yeah.
So, I saw him, but I wanted to check with you first.
Okay, so can we do that after the yeah. Sorry.
Yeah.
Okay. Now, what were the zero modes of B? The zero modes of B were the zero modes of the operator del bar acting on B. Okay? These are zero modes of the operator del bar. So they are all holomorphic modes. But they are holomorphic modes that preserve the periodicity of the torus. There is no holomorphic mode that preserves the periodicity of the torus other than the constant. It's very similar. Do you remember how we computed the zero modes of on the sphere? Okay, do you remember how we did that? What we said was we looked at all holomorphic modes of B, but that were well defined all over the sphere. That the analog of that is preserve the periodicity of the torus. Got the same for C. So both B and C are constants. Yeah.
So I had a simpler argument for why this should be the zero mode.
Yes.
Is that you have d2w, bw and nothing else in the insertion.
Yes.
Given that it's only b of w, should it just automatically pick out the constant piece? Is that too stupid an argument?
Given that it's only B of W,
You just automatically pick out the constant units.
you're saying just as proper Fourier transforms. That's what you're saying?
Yeah.
But you see, what I want to argue, you're right that this Fourier transform, just picks out the average part of this, is what you're saying. But what I want to argue is that this, inside the integral, I can change the insertion point of this. So forget about the integral. Okay? Even without the integral, that B of W insertion doesn't depend on where you what W is. That's what I look at. Okay? So imagine the integral wasn't there. Because then I'm going to do the integral.
Okay.
So even without the integral, insertion of B of W is independent of W.
Okay.
Therefore, I can replace it by the insertion of B of 0.
Okay.
And take it outside the integral.
Oh. Just same as picking out the average and pulling it out.
No, but the average is the insertion B of 0. That is insertion at a particular point. Yeah, so of course you could define this as integral B of, you say we could define B bar as the average insertion of B over all points divided by volume times volume. You could do that. But what I want to say is that in this particular case, that definition is the same as inserting just B at a point. That is not always true. Right? Okay. So what we got here is this. This can be replaced by the insertion of B of 0, B bar of 0, and these two guys, this volume divided by 2 pi I tau 2, just becomes volume of the torus divided by 2 pi I tau 2. I'll call volume of the torus 4 tau 2 square. I'm keeping the 4s just for fun because it's not going to cost a factor. And volume square. Okay? Excellent. Now, the next thing is this V. You see, I'm going to make this formula as I already have C of 0, C bar of 0. That's nice. C of 0, C bar of 0. Now, the next thing about this is this fixed vertex operator. Got it?
By putting everything at 0, now you will be everything dependent on the order you put this.
You up to sign.
So C and B have neutral operator.
What?
C and B have a neutral anti-operator, right?
C and B have a non-trivial anti-operator. This is true. Yeah. This is true. I think it's just you see, all of this in some sense is fake. Because all of the insertions, as you say, at a given point are proportional to the insertions of the 0 mode. And you imagine expanding this like we've done here. It's only the 0 mode that contributes. So, all of these, if you want in your mind, is replaced by 0 mode insertions. C0, C0 bar, B0, B0 bar. Okay? Now, it's true that these guys have anti-commutators. So now your point once again is what about the C0, C0, B0 anti-commutator? What about the C0, B0 anti-commutator? And you know, what's going to happen is, yeah, yes.
Alright, the part that becomes anti-commutator is disappears because of positivity.
Yeah, that's probably right. That's probably right. Yeah, exactly. Good. That's exactly. Thank you. So you could say this even without hitting the zero. Yeah, the part that is a constant just disappears because there is no zero work. Exactly. Thank you. That's the perfect thing. So it's unambiguous, even though it looks ambiguous. Thank you. Okay, excellent. Wait. So now we've got this, but we've also got the integral over this. We've got this fixed vertex operator. I'm going to make the whole formula really democratic. So the fixed vertex operator, this origin. So though I put this originally as 0, I could have put this at some w. Now, even the point, of course, was that the abstract formula, the w you insert, the c sat, have to be the same as the w you insert, the vertex operator. But because the c0 mode is constant, okay, this insertion can be independent of the insertion of v, be changed to an arbitrary insertion. So instead of inserting, so let me tell you the argument. Oh, this has taken much longer than I hoped. Let's see if we can do it. Yeah, you see, the fixed vertex operator, we could have inserted c bar w, c of w times v of w at any point. We could then have integrated this over the volume of the torus, dividing by v2. Okay? We could have done that. Now, because by an independent argument, namely the constancy of the C0 modes, this is independent of W. This could just be replaced by C of 0, C bar of 0. So we get this with this now this fixed vertex operator replaced by an integrated vertex operator by V of W. Okay? So now what is the final formula? The final formula is C0, C0 bar, V of 0, B0 bar, all vertex operators integrated. Okay? Times factor V2 squared by 4 tau 2 squared times 1 over V2. Is this clear? Is this clear? Not clear. Okay. Did you see how I went from this to the integrated vertex operator? You see that required a division by V2. So this now became an integrated vertex operator, but there was a 1 over V2. So we have these factors that were left over, and there is a 1 over V2 from this. Every operator has become integrated here, and these insertions were C0, C0 bar, B0, B0. Tell me what's happening here.
Why is it C0, C0 bar?
Why not CW, CW? It's because the insertions of C's